Okay, good morning students. In the previous lecture, we have studied the streamlines and sketches of the field, right? And that was the last topic in that chapter, that is unit 2. Then next we have started with unit 2, chapter 3, right? Electric flux density, Gauss law and divergence. And in this chapter, we have already covered what is electric flux density, right? And we have seen what is the difference between electric field intensity and electric flux density, right? D and E, right? And the relationship between D and E, right? D equal to epsilon naught E. And we have established the formulas for D due to point charge, line charge, surface charge and volume charge, right? Okay, in today's lecture, we are going to study the Gauss law, the mathematical form of Gauss law, or the mathematical representation of the Gauss law, and the proof of Gauss law, and we'll solve few numericals based on that. And in the previous chapter, we have derived the electric field intensity due to point charge, line charge, surface charge and volume charge by making use of Coulomb's law, right? Here, instead of that, we will be making use of Gauss law in order to find out the electric flux density due to point charge, line charge, surface charge and volume charge. If we find out electric flux density, it is as good as finding electric field intensity because we know the relationship between D and E. D is equal to epsilon naught E. If I know D, I can calculate the electric field intensity. If I know E, I can calculate the electric flux density D, right? Okay. Then, yes, already we are familiar with Faraday's experiment, what he has conducted, right? He has taken the sphere of smaller radius, right? And it is charged plus Q. And he has taken the bigger sphere, right? Concentric spheres means the sphere embedded within another sphere, right? Concentric spheres. This we have seen. These two are metallic spheres. In between them is the dielectric material or media that we have seen. Then the outer sphere is induced with charge minus Q, right? This we have seen. Then what Gauss has observed is it is not mandatory that the outer sphere should be present, metallic sphere should be present, or it should be, right? So, or the inner sphere should be spherical in shape, the charge should be spherical, something like that, right? What he has generalized, right? But he has retained the outer Gaussian surface. This is the Gaussian surface. So Gaussian surface, yes, I'll write the Gaussian surface. The surface which encloses the charge, we call it as Gaussian surface, right? And Gaussian surface is a imaginary surface, right? And it is a closed surface. And there are some restrictions how we should choose this Gaussian surface. Everywhere the flux lines or field lines should live normal to the considered closed surface. It should be normal everywhere. I should choose the closed surface in such a way that everywhere the field line should live normal to it. Then we will try to enclose the charge here. Yes, it should not, it is not mandatory that it should be this only, right? It can be point charge plus Q, right? Yes. And another extension, yes, once again he has chosen the Gaussian surface, right? Then instead of point charge, some volume charge is considered. It may be volume charge, right, plus Q. And this is Gaussian surface. Gaussian surface is the imaginary surface. It is not mandatory that metallic sphere should be there, right? It's a Gaussian surface. Means we want to find out the total amount of flux lines leaving this Gaussian surface. Here, the total amount of flux lines reaching this outer sphere we have studied. Here, the total amount of flux lines leaving this Gaussian surface, right? Psi equal to Q. Already the Faraday has told it, right? The amount of the flux lines leaving the closed surface is equal to the total charge enclosed by that Gaussian surface, right? Enclosed by the closed surface, right? That we have seen. So it is not mandatory. It can be point charge, it can be line charge also. It can be line charge having line charge density rho L. It can be some surface charge having surface charge density rho S. It can enclose all the three types of charges. It can be volume charge also, right? It can be anything, right? And not only that, it should be symmetric in nature. Let me take the brass key. Let me assume that it is positively charged everywhere. Then I will enclose this within the closed surface, Gaussian surface, right? This also holds good. This is plus Q, right? So the total amount of flux lines, the electric flux lines leaving the closed surface psi is equal to the total amount of charge enclosed, right? He has extended the Faraday's experiment and he has generalized it, right? Generalization of the Faraday's law led to the Gauss law, right? We will see the mathematical form of Gauss law and representation of it, and we'll go see the proof of the Gauss law also, right? Yes, the statement of the Gauss law goes like this. The electric flux passing through any closed surface is equal to the total charge enclosed by that surface, right? Psi equal to Q. We know this. Then we will try to obtain the more mathematical expression or representation of the Gauss law. Right, this is the mathematical representation or mathematical form of the Gauss law. Psi is equal to closed. This circle indicates closed and S indicates surface. Closed surface integral of ds dot ds. ds is electric flux density and ds is the surface area over which the flux lines are living. This is the closed surface, right? So psi is equal to the closed surface integral of ds dot ds, and that is equal to psi equal to q, we know. So that should be equal to the charge enclosed q. So we will try to prove how this psi is equal to surface integral. We will try to obtain this mathematical form, how it will come. We will see it. Already I have drawn the diagram. So how to obtain the mathematical form of Gauss law or representation of Gauss law? We will try to make use of the definition of the electric flux density D, right? Okay, we will consider the Gaussian surface here, right? It is amoeba shape, it can be any shape, right? We have considered some Gaussian surface, right? Gaussian surface is a closed surface and it is an imaginary surface, right? I should choose the Gaussian surface in such a way that everywhere the flux lines should leave normal to the considered Gaussian surface. And let me assume that this Gaussian surface is enclosing the group of charges here. Can observe here, right? Set of group of point charges plus q, right? So it is this Gaussian surface is enclosing the set of point charges here. Then this is the bigger closed surface. Let me consider the smaller surface here. You can observe here, this is the smaller surface and it is ds vector. Smaller surface we have considered. Is it fine? Then we will consider the unit normal vector. Means unit normal vector means it is normal to the considered surface, that is an vector in this direction. An vector, this we call it as unit normal vector. And this is the group of charges. Everywhere the field lines are living in all the directions, but we will consider this small surface, and you can observe the flux lines are crossing this smaller surface in this direction, right? ds vector, and this ds vector, it is making some angle theta with respect to the normal, right? Okay, I hope we have understood the scenario. Then we want to find out the numbers, the smaller amount of flux lines leaving this smaller surface. Smaller surface means ds vector, right? So this ds vector is equal to the surface area ds and the unit normal vector an. Means we have chosen in such a smaller surface that that unit normal vector is normal to this considered surface. So ds vector into an, right? Okay. And I want to find out the component of this electric flux density in the normal direction. Every vector has two components, horizontal component and vertical component. This, let me consider this as vertical component, that is the normal component. So the component of the electric flux density ds vector along this unit normal vector is, let me call this as ds normal, right? Okay, we'll start the derivation. Yes, the definition of electric flux density goes like this. D is equal to, just I will not take the vector, just I will take the magnitude. The electric flux density is equal to flux passing through unit surface area, psi by s actually, right? But why we have written d psi by ds means we have considered the smaller surface. Smaller surface means small amount of flux lines will be leaving this smaller surface. Hence we can write d psi by ds. And d psi is equal to d dot ds. This is the smaller amount of flux lines crossing the closed surface or Gaussian surface, right? Then d psi is equal to, what is this d, right? The component of ds vector along the normal direction, that is ds normal. So instead of d I will write ds normal. So d psi is equal to ds normal into ds. Is it fine? Then what actually this ds normal is? Means we are taking the projection of this ds vector onto this an vector, unit normal vector, right? Take the projection of this. So take, means what is ds normal? Ds cos theta. This is ds, right? If by geometry ds cos theta, if I take in along this unit normal vector ds cos theta. So this ds normal is nothing but ds cos theta. This ds normal is nothing but ds cos theta. Take the projection of ds vector in the unit normal vector direction, right? So ds cos theta into ds as it is. Then we know we'll take the help of the dot product. So we can write this as ds vector dot ds vector. So just apply this dot product, we'll get back this. Observe here, magnitude of ds, magnitude of this small ds into cos of the angle between them, right? So cos theta. I hope you right. So the dot, we can write this d psi as the magnitude, the dot product of two vectors, ds vector dot ds vector. But this is the differential electric flux lines that is crossing the smaller surface, but I want to find out the total number of flux lines leaving the closed surface. So integrate it. So psi is equal to integrate over the entire surface, closed surface integral of ds dot ds. The same thing has been written here, closed surface integral of ds dot ds, and that is equal to charge enclosed q. So this is the mathematical form of the Gauss law, representation of the Gauss law. If I integrate over the entire surface the amount of electric flux density over the entire surface, then it is equal to the amount of flux lines leaving, or it is equal to the charge enclosed, one and the same. I hope you understood the meaning of this statement, right? Yes, we'll try to generalize. Already we have seen the Gauss law. We'll try to make it more general, right? So this is the Gaussian surface what I have drawn, and it is enclosing these four types of charges: q1, q2, q3, q4. What is q1? I will tell you. It is a group of point charges, summation of q1. Group of point charges is q1, means I have group of point charges like this. I have not shown in the diagram here, right? Group of point charges q1. Next I have the line charge. Yes, I have the line charge having the line charge density rho l, right? And q2 can be calculated as line integral of rho l dot dl, right? Then q3 is the surface charge. Let me take one surface here, smaller surface. So its surface charge density is rho s, and surface integral of rho s into ds, that is q3. Then let me consider volume charge q4, some volume, any volume you can consider, but I am taking a cubical volume here. So q4, volume integral of rho v into dv, that is q4. Is it fine? Okay, this Gaussian surface is enclosing these four types of charges. Then we know the number of flux lines, the total electric flux lines crossing this closed surface psi is equal to the total charge enclosed. Means it is enclosing all the four types of charges. So add them, q1 plus q2 plus q3 plus q4, that is psi. Is it fine? I hope you understood this. But see, there are point charge, line charge, surface charge, volume charge. We can look at all the types of charge distribution as volume charge only. If volume charge shrinks, means you have certain volume. If it shrinks to zero, it becomes a point charge, right? So we can look the other types of charges, that is point, line and surface, as a volume charge only. So finally I can write the equation as, you can observe here, psi is equal to the mathematical form closed surface integral of ds dot ds, and it is equal to, I am treating the group of charges as volume charges, so volume integral of rho v into dv. I can write this now. Yes, I hope you understood this. So psi is equal to closed surface integral of ds dot ds, that is equal to q. But this q, what is this q? I am treating this charge, the enclosed charge, as volume charge. So q is equal to volume integral of rho v into dv, right? So I am looking at all the other types of charges as volume charge only, right? Yes, I have written on statement here, net flux
Excuse me,
for
sir.
the, yes, you can unmute yourself and ask
Sir,
without.
you are not able to join the class, sir.
Yes,
If you are
yes.
not able to join the class, sir, would you allow them in?
Why? What's the problem? In all these days you were able to. 1 minute, just I'll check. 1 minute. Wait. So they are joining now. Yes, they are joining. Yes, they are joining. Auto admit option I have set. Okay. Next, we will consider the Gaussian surface here. But this Gaussian surface is not enclosing any charge here. There is no charge present in this Gaussian surface or closed surface. Okay, but we have considered the charge outside this Gaussian surface. Plus, it may be point charge, line charge, surface charge, or volume charge here, right? Then we have made one statement here: net flux over the Gaussian surface is zero, because here, right, everywhere the flux lines are living in all the direction. Yes, it here in this direction the flux lines will enter this Gaussian surface, and they are leaving this Gaussian surface. Means flux entering the Gaussian surface is equal to the flux leaving the Gaussian surface. So flux entering is equal to flux leaving the Gaussian surface, means the net flux over this Gaussian surface has to be zero, right? So this statement holds good. Whenever the charge is outside the Gaussian surface, the net flux over the Gaussian surface is zero, because the flux entering the Gaussian surface is equal to the flux leaving the Gaussian surface, right? Okay, fine. Next, we will see the proof of Gauss law, right? Already we have this Gauss law, psi is equal to surface integral of ds dot ds, and it is equal to q. We have to prove this, right? So this is LHS left hand side, and this is RHS. So I will take LHS and we will try to prove it, right? So take LHS left hand side, closed surface integral of ds dot ds. And in order to prove the Gauss law, what I will take? I will take the point charge which is lying at the origin of the spherical coordinate system. I will take the point charge which is lying at the origin of the spherical coordinate system, and the Gaussian surface which shoots the point charge is spherical surface enclosing that point charge. So I will draw the diagram. Later on you can observe this diagram. So I will draw the diagram here. X, Y, Z. So spherical surface I am drawing, but what I am drawing is 1/8 of a sphere. It should be complete sphere actually. So this scenario, just observe here, there is a point charge at the origin of the spherical coordinate system, and this is the Gaussian surface. It should be a sphere, right? So this is the Gaussian surface. But in this diagram, I have taken only 1/8 of a sphere. 1/8, cut it into 8 pieces, right? 1/8 of a sphere. So just observe the diagram here, what I am drawing carefully. Yes. So this is the surface, right? Then I will consider the smaller surface here. Right, smaller surface, and here point charge q is at the origin of the spherical coordinate system. The flux lines are living in this direction, and ds vector, it is normal to the unit normal vector an, and ds is also living in the same direction. It is in the radial direction. The flux density is also in the same direction as that of unit normal vector an vector, because it is normal to the given surface, right? So the flux lines, so it is living like this, and the radius is r, and this is making angle theta with respect to z axis, and radius is r. And you can observe this, if I move from this side to this side, the angle is phi, right? Along this with respect to x axis we measure. So we are taking the help of the spherical coordinate system. We have all the three coordinates r, theta and phi, right? Then next, what is ds and what is this ds, small ds, we will see. So we know that the electric flux density due to point charge, already we know the formula. The electric flux density ds due to point charge, it is given by q by 4 pi epsilon naught r square into ar. But epsilon naught should not come into picture. It will come in the electric field intensity. E is equal to q by 4 pi epsilon naught r square, because d equal to epsilon naught, we know, right? Epsilon naught should not come into picture. But let me assume that the radius r is a, or else I can leave it as r only, no problem. Let me assume the radius is a, r equal to a, right? So I'll substitute here q by 4 pi a square into ar, right? Next, this ds is over. Next, what about this differential surface area ds? So differential surface area, see here, everywhere the field is living normal to the spherical surface. Everywhere the field is living spherical to the normal surface, right? It is normal to the spherical surface. It is in radial direction. So ds, it should be, yeah, this is normal means it is in radial direction. So differential surface along radial direction ds r. And we know the differential elements in spherical coordinate system. I will write here dr r d theta r sin theta d phi. These are the differential elements, dr, d theta, d phi, angular distance r d theta, angular distance r sin theta d phi, right? So I want differential surface area along radial direction. Leave this and multiply other two. So r square sin theta, r square sin theta d theta d phi, d theta d phi, but associate the direction, it is in radial direction. So ar. Is it fine? So here an is equal to ar, it is in radial direction. Unit normal vector is an, that is equal to ar, it is in radial direction. So we came to know what is ds, what is ds. So we will take LHS and substitute, and we will proceed with the calculation. So closed surface integral of ds into ds is equal to, so this ds ar dot ar will be 1. But what about r? R is nothing but, substitute a here, It is a square. R square is nothing but a square. So I will write once again here a square sine theta d theta d phi ar. Okay, just I will write it below equal to. Okay, closed surface integral is double integral. So double integral of. So what is q by 4 pi a square? Ar dot ar is 1, so I will not write q by 4 pi a square into this ds a square sine theta d theta d phi. This ar dot ar is 1, I will not write. So we have to integrate along theta and phi. Theta, it is varying from 0 to pi. For a sphere, we know the limits of theta and phi for the spherical surface. Theta is from 0 to pi and phi is from 0 to 2 pi. A square will get cancelled. So next we'll integrate it. So q by 4 pi is constant, I can take it out. Q by 4 pi is taken out. So it is taken out. First I will integrate with respect to phi. I will open bracket. So phi is constant. So phi, it is varying from 0 to 2 pi. Next I will integrate with respect to theta. Integration of sine theta is minus cos theta. And limits of theta is 0 to pi. So from this I will get 2 pi. Q by 4 pi. From this I am getting upper limit 2 pi minus lower limit into. So from this what we will get, we'll see minus as it is. So cos pi is minus 1 upper limit minus lower limit cos 0 is 1. So minus 2 minus 2 minus 2 minus plus 2. So into 2 I will get. From this I am getting 2. This I am taking it here, right? So 2 to 4 pi will get cancelled. This 4 pi will get cancelled. I am left out with q. So LHS, what is LHS? Closed surface integral of ds, I have to write s here, ds dot ds is equal to q, right? So we have proved the Gauss law. I hope you understood this, right? The closed surface integral of the electric flux density over the closed surface is equal to the charge enclosed, and it is also equal to psi. Psi is equal to closed surface integral of ds dot ds equal to q, right? One and the same. I hope you understood this. Next, we will solve few numericals based on the Gauss law, right? And electric flux density. Given the electric flux density D vector is given 0.3 r square ar nanocoulomb per meter square in free space, and there are three parts in this problem. Part A, find the electric field intensity E at point P of r theta phi. They are given 225 degree, 90 degree. First we'll take up one by one. Part A. Yes, D vector is given. Write down 0.3 r square into ar nano. Nano means 10 power minus 9 nanocoulomb per meter square. This is given. Then find E vector at point P. We want to find out what is electric field intensity E at point P of 2, 25 degree, 90 degree. Right? We know the relationship between D and E. If I know D, I can calculate E. If I know E, I can calculate D. D equal to epsilon naught E. You know this relationship, which implies E is equal to D divided by epsilon naught. So D we have here 0.3 r square, 0.3 r square AR, right? Nano. So what I will do, 0.3 r square. What is R? R is nothing but r theta phi. R is 2. So r square means 2 square. 0.3 r square is nothing but 2 square. Into 10 power minus 9 I will take this nano. This nano I will take 10, and then I will write AR divided by epsilon naught is 8.854 into 10 power minus 12. So calculate this. So 0.3 into 4, 2 square is 4, exponential 4 exponential minus 9 divided by 8.854 exponential minus 12. So I am getting it as 135.53, 135.53 AR. So volt per meter for electric field intensity, right? So part A you can verify, this is fine. Next we'll move to part B. Find the total charge within the sphere r equal to 3. So we want to find out what is the total charge q. The radius of the sphere is 3, right? Then psi is equal to q. We know this, psi is equal to q, right? So we know the formula. The electric flux density leaving the closed surface is equal to the total amount of charge. Either find out electric flux or find the total amount of charge. One and the same. Both are one and the same. They may ask total electric flux or they may ask total charge enclosed. Both are one and the same, right? Then next we know the formula. Psi is equal to q and they are given d. D is given. So it is equal to closed surface integral of ds dot ds. I can write this simply as d vector, but ds indicates it is crossing the electric flux lines crossing the given closed surface. That so hence we have written yes here. That's all. So what is this ds and what is this ds? Once we know, then problem is left out with only integration. So first we'll write what is ds. Yes, we don't know what is the point charge or flux lines, right? ds is given, that is 0.3 r square. It is given 0.3 r square ar nano coulomb per meter square. But r is 3. You can substitute r equal to 3 here, but I will not substitute now because part c also is helpful. R equal to 4 they are given, part b, so I will keep it as it is. Then next, so you can observe the electric flux density, or AR means it is only in radial direction. If I consider a sphere, the field lines are living everywhere normally to the considered Gaussian surface in the radial direction, right? The unit normal vector is the AR. So what is this ds? It should also be in radial direction, dsr. So in the previous problem we have studied what is dsr. So this I have taken dr, r d theta. These are the three differential elements. If I want dsr, multiply other two, right? R square sin theta d theta d phi. R square sin theta d theta d phi into ar. Then take the dot product of ds dot ds and integrate it, right? So psi equal to q, that is equal to closed surface integral double integral, right? Ar dot ar will be 1. I will not write. So other things I will multiply. R square into r square, it will become r to the power of 4. 0.3. This nano I will write it as 10 power minus 9. 10 power minus 9. R square into r square is r to the power of 4. Then this is taken care. Ar nano is taken care. Here r square is taken care. Sin theta is left out. So sin theta d theta d phi, and I have to integrate along theta and phi direction. Theta for spherical surface, theta is from 0 to pi. For spherical surface, phi is from 0 to 2 pi. So take the constants outside. 0.3 into 10 power minus 9. Even r power 4 is also a constant because we are integrating with respect to theta and phi. R power 4 is taken out. So next integrate it. So directly I will integrate. First I will integrate with respect to phi. Phi is a constant and it is varying from 0 to 2 pi. Next I am left out with sin theta. Integration of sin theta is minus cos theta. So limits of theta is 0 to pi. So I will write 0.3 into 10 power minus 9 r to the power of 4 into, from this I will get 2 pi, upper limit minus lower limit. From this I will get 2, right? Already we have calculated in the previous thing, I know it, so I will get 2. Is it fine? So next multiply 2 to the 4 pi into 0.3. 4 into pi into 0.3. So I am getting it as 3.769 into 10 power minus 9. I have multiplied 2 to the 4 pi into 0.3. I have multiplied this and this I have multiplied. So 10 power minus 9 as it is, r to the power of 4. So this is psi equal to q. But what he has given r is 3. So put r equal to 3 here. Put r equal to 3. So I will getting the charge enclosed q is equal to 3.769 exponential minus r, else I can leave that like that only, 10 power minus 9 into r to the power of 4. 3 to the power of 4. R is 3. 3 to the power of 4. So I am getting it as 305. 305 into 0.289. This 10 power minus 9 is there. I will write it as nano coulombs, right? So you can observe 305 nano coulombs, right? Then coming to the part C, what they have asked, find the total electric flux leaving the sphere of r equal to 4. Total electric flux means psi and it is equal to q. Calculate at r equal to 4. Observe the previous problem. R equal to 3, R equal to, substitute R equal to 4. Put R equal to 4 in the above equation. Put R equal to 4. So that will be the answer for part C. Psi equal to Q, and that is just calculate. Instead of 3 to the power of 4, what we have to do? 4 to the power of 4. 4 to the power of 4. Multiply with that. So I am getting 964.86. 964.864. 10 power minus 9 is there, nano coulombs. So 964, they have rounded it to 965. 965 nanocoulombs. I hope you understood this, right? Yes? Okay. Okay, last problem of today's class. And okay, then this is a conceptual problem. If you understood whatever we have studied in the today's class, you can easily solve this. It is based on the concept, right? So we'll try to solve it. Calculate the total electric flux leaving the cubical surface. Yes, the surface is cubical surface formed by 6 planes. Yes, cubical surface has 6 planes, and the limits put on the xyz, they are varying from plus 5 to minus 5, minus 5 to plus 5, or plus or minus 5. And if the charge distribution is, there are three parts, part A, part B, part C. We will take up one by one. Part A, 2-point charges, 0.1 microcoulomb is located at this point and 1 by 7 microcoulomb is located at this point, right? Okay, and cubical surface, whether these two charges, 0.1 microcoulomb and 1 by 7 microcoulomb, whether they are enclosed in the cubical surface or not. If they are enclosed, then psi is equal to q, right? That is the thing we have to calculate. So part A, I will take up. So one of the point charge, let me call it as q1, and it is equal to 0.1 microcoulomb, and it is at, let me call this as point A of 1 comma minus 2 comma 3. And another charge q2, let me call it as q2, 1 by 7 microcoulomb, and it is located, let me call this as b of minus 1 comma 2 comma minus 2. Yes, and cubical surface is formed. Let me draw the cubical surface. Okay, I'll draw it here, but I'll not take the help of the coordinate system. Just I'll draw the cubical surface. Right, just I'll draw the coordinates outside. Means this side represented is along x direction, it is along y direction, and it is along z direction. Here this represents x. X is varying from minus 5 to plus 5. Minus 5 is here, plus 5 is here, and this side is y. This is y. Y is minus 5 is here and plus 5 is here. Minus 5 to plus 5, and z, minus 5 is here, plus 5 is here. Z is varying from minus 5 to plus 5. So the limits x, y, z, they are all lying between minus 5 to plus 5. Minus 5 to plus 5. I hope this is the Gaussian surface. Gaussian surface, which is the closed surface, is given, and the charge distribution is given, q1 and q2. Whether this q1 and q2 they lie within the cubical surface or not, just by looking at the points we have to say. Observe the point A, 1 comma minus 2 comma 3. Yes, the value of x, y, z, this is x, y, z. They are all lying between minus 5 to plus 5, means the charge q1 is lying within. Q1 is within this cubical surface. Next, observe this q2 minus the coordinates x, y, z. They are also between minus 5 to plus 5, means both the charges q1 and q2 are lying within the cubical surface. Then by the concept we know that part A, that the total amount of flux lines leaving this closed surface is equal to the total amount of charge enclosed, q total. So q total is nothing but the two charges q1 plus q2. q1 plus q2. So q1 is 0.1 micro plus q2 is 1 by 7 micro. So add them. So that will be your the amount of flux lines psi leaving the closed surface. So 0.1 plus 1 by 7, 1 divided by 7. So 0.1 plus 1 by 7. So 0.242. 0.242 0.2428 microcoulombs. You can observe 0.243 they have given 0.2428, right? It's correct. Next, coming to the part B. A uniform line charge of pi microcoulomb per meter at x equal to -2 and y equal to 3. Yes, we will try to draw this uniform line charge. Try to locate it. X, y, z. So x is -2. X is -2 means somewhere it will come here. X is -2. Then y is +3. Y is +3 they have given. Y is +3 means just will move in the forward direction by 3 units along y direction. It will come here. So x is -2 and y equal to, so I'll extend this y axis, and it is parallel. This line charge is parallel to z axis, and this line charge density rho L they have given pi microcoulomb per meter. Is it fine? So it is parallel to z axis. Then next, observe here, it is parallel to z axis. Whether this line charge is enclosed within this cubical surface or not. How much amount of line charge? Somewhere it is coming here means just I will draw the line charge, and this is rho L, that is pi microcoulomb per meter. But it is infinite means it is coming out of this top surface and it is coming out of this bottom surface. But how much amount of charge is enclosed? So it is all varying along z axis from -5 to +5. Z is -5 here and z is +5 here. Total distance is 10 units, right? So I have to I know the definition of line charge density rho L equal to charge per unit length. Charge per unit length. I want to find out the total amount of charge enclosed in this cubical surface. So Q is equal to the line charge density rho L into length of the line charge. The length of the line charge is from -5 to +5. I should not consider the line charge outside this top surface and outside this bottom surface. I have to how much amount of charge line charge is enclosed within this, right? So Q that is also equal to psi. Both are one and the same. Rho L is how much? Pi micro. Pi into 10 power -6. Pi micro coulomb. Then what is the length? Length of the line charge. That is 10 units. So pi is 3.14. 10 into 3.14. Right? So just multiply 10 into pi. So I am getting it as 31.41. So psi equal to Q. That is equal to 31.41. This 10 power -6 I will write it as microcoulombs, right? So 31.41, right? So part B is over. If any doubts, you can unmute yourself and you can ask me at any moment so that I can clarify immediately, right? Part C, it is very important and you have to understand it, right? Calculate the total electric flux leaving the cubical surface. Fine. Part C, a uniform surface charge of 0.1 microcoulomb per meter square on the plane. They have told plane y equal to 3x. It is not a straight line. Y equal to mx. Don't think like that. So it is a plane y equal to 3x. So we will try to picturize it. We'll solve part C here. The surface charge density rho s is given how much? 0.1 microcoulomb per meter square. 0.1 microcoulomb per meter square. Then y equal to, it is on y equal to 3x plane. So y equal to 3x plane. We will try to draw that plane. So I'll take only x axis and y axis. I will not consider the z axis. And we know that the limits are put on x, y, z. We know this. Cubical surface, all they lie between -5 to +5. We know this. We have to keep this in the mind. So let me take x here. Let me take y here. Maximum value of y it can take is -5 to +5. So let me take +5 here. +5. If y is equal to 5, then what is x? 5 by 3. So corresponding to this, when y is 5, x is 5 by 3. So x is 5 by 3 plus 5 by 3. Is it fine? When x is 0, y is 0. When x is having some value, just the line goes like this. Just I'll draw the diagonal. Right? So this is 5 by 3, this side is 5 by 3, this height is 5. Then we can calculate this, right? Hypotenuse. So calculate it. Under root of 5 square. Under root of 5 square is 25 plus 5 by 3 whole square. 5 divided by 3 whole square. So after calculation, we get it as 5.27. This side, 5.27 we are getting. Yes, the value of y can vary from minus 5 to plus 5. Till plus 5 we have seen. Minus 5 somewhere we'll take it here, minus 5. And whenever value of y is minus 5, I will get x as minus 5 by 3. Right? So extend this. So the line goes like this. Is it fine? So not double line, it is single line. Okay. This height is 5 and this height is 5 by 3. Calculate the hypotenuse. Once again it is 5.27. But this is a straight line, but this is not y equal to 3x, it is not a plane, just it is a straight line. But plane means, just observe here, this group of lines will form a stack along z-axis. Z-axis, it appears like a point here. This is y-axis, this is x-axis. Z-axis is perpendicular to this x and y, means it is coming out of the computer screen or your mobile screen, right? Z-axis will come out. So z will vary from minus 5 to plus 5, right? So I will draw this y equal to 3x plane, how it will form, just observe it. I am doing my best to make you understand this. Okay, only thus 5.27, 5.27. Add this 5.27 plus 5.27 so that from here to here I will get total length. Means this side 5.27 into 2, 5.27 into 2. So I am getting it as 10.54. This side, this is 5.27 plus 10.54. But it is y equal to 3x plane. So just extend it. It is along z axis. Z is varying from minus 5 to plus 5, right? So this side, so 5 to 5, 0, minus 5 to 0, 5 units, 0 to 5, totally 10 units, right? So this is the surface area and its surface charge density rho s they have given. It is how much? 0.1 microcoulomb per meter square. 0.1 microcoulomb per meter square. So this is the surface charge that is enclosed in this cubical surface. This is the cubical surface, right? So this is the surface charge that is enclosed in this cubical surface, right? So we know the surface charge density for a definition: charge per unit surface area. What they have asked? They asked to calculate the total electric flux psi. So which implies Q is equal to rho s into the surface area, and psi is equal to Q, that is equal to rho s into s. Rho s is given, fine. What about the surface area? Just multiply the two sides, 10 into 10.54, right? So we'll substitute rho s is how much? 0.1 micro means 10 power minus 6 into surface area is multiply two sides, 10.54 into 10. So 10.54 into 10. So psi equal to Q, how much we will get? We will calculate. So 0.1 into 10.54, 10.54 into 10. 0.1 into 10.54 into 10. This I am doing. 0.1 into 10.54. This 10 power minus 6, we will take it later. So we are getting 10.54. 10.54. This 10 power minus 6 is nothing but microcoulombs. Right, this is the total amount of flux leaving the closed surface, or this is the total amount of charge enclosed in that closed cubical surface, this cubical surface, right? So 10.54 microcoulombs. You can observe the answer here. Is it fine? I hope you have understood this. If any doubts are there, you can unmute yourself and talk to me so that I will clarify the doubts immediately. Okay, this is the homework problem. You do it, because already this type of problem we have solved here. Okay, here first problem only, this one, right? This problem we have solved. Similar type, it is given here, you try to solve it, right? I hope you will do this. So I'll stop my today's lecture here. I'll stop.